Give me a second. And I'm going to talk about how we can use simulations to evaluate things. And we can use simulations when we, how to phrase this. So let me go back to something I've said before. Can you roll up the screen for me? No, never mind. I want to use the board for about 5 minutes. So can you get it ready for me? Or, So we talked a lot about this equation here, which is the solution to the normal. Here we have stuff that depends on the observations, and then we have the normal matrix. We take the inverse of it, and that gives our estimates. And one of the questions you're being asked is, what happens if you have noise? And when you have noise, you have B goes to some B plus delta B. This is due to the noise here. And that means that A is going to go to A plus delta A, where delta A equals n to the minus 1 delta B. So the change in A depends only on the change in B. And the normal matrix doesn't depend, it depends on what observations we make, but it doesn't depend on the magnitude of the observations. So we can know the normal matrix, we can set up the normal matrix. We know what the normal matrix is before we do the experiment, basically. So one approach to doing things in VLBI is saying, I am going to assume that my observations have noise, some delta B there, then see what the effect is on the delta A. So I will do, and I'll do this a whole bunch of times. So I'll have delta B1, delta B2, delta B3, et cetera, all the way down to delta Bn. And these delta B's can be different things. I'm going to assume that they are random in some way. And so delta B1 is going to give me some change in A. Delta B2 is going to give me another change in A. all the way down to here. And if I look at the variations here, this tells me how sensitive I am to changes here. So ideally, what I'd like is, if I make changes here, I don't want it to affect this much. So that's sort of one thing we can check. The other thing we can do is, we can say, suppose that I change the way I'm doing my estimates. I talked about how we estimate clocks and atmospheres as a piecewise linear function with, I assume that my atmosphere goes like this, like that, with breaks every hour. I can say, suppose I put the breaks every 3 hours. What's the effect going to be here? So I can investigate different ways of parameterizing the data without actually taking the data. And this is useful because taking the data is expensive. And anything that we can do to make things better without actually taking data is worthwhile. So I wrote a program called Simple Simul for simple simulations that we're going to use. And what we're going to do is we're going to take some schedules and then we're going to run it through the simulation program. And the way the simulation program is set up is that it will do 1,000 simulations. And then it will calculate what the average change in A is, or what the RMS change in A is. So that's a way of evaluating how good things are. Now, we use this at NASA when we are, and we'll say, what happens if I use this network instead of that? So that's one of the ways we use it. Or what happens if I use 10 stations instead of 7 stations, and so on. So we're just going to go through some examples of that. And then we'll discuss them. And I think that's probably will be it for today. So just wanted to give you guys a heads up about what the concept is. Any questions here? No. Okay. Crystal clear. So we're going to start off by, I want you to get the following schedule files from CDDIS. So we need a site that has the information. And I'm going to type a list here of the schedule files, but you can log on to the website in the meantime. So this is, I'm telling you, what the year is that this schedule file should be found. And then that's the schedule file name, R1258, R4158, etc. And I'm going to do the first one with you guys so that you can see how to go about doing it. So we go to the IVSCC website. Go to Data and Projects. And click on All Master Files. So the first one is from 2007. So we're going to click on HTML07. Let me know if you guys are there. So what did I say? This one was R1258. So that's this file there. So click on that link. And it will have this link to everything there. And one of the links is the schedule file. So click on the schedule file. And then it's going to ask us for a password. So is everybody okay?
After the download, I need
Pardon?
after
Download all of these schedule files. So there's like this list of 4 over here.
Some way to find the second one is the 2012.
So it turns out I was wrong about the second one. Ignore the second one for right now.
Okay.
I'll tell you, I was wrong about the year. Second one we're going to use. Hi. Okay, I put up, I revised the list. Uh-huh.
Your screen. Nice. Okay.
Okay, thanks.
Awesome.
So Max, what I was telling people, are you going to try to follow along or not?
Okay. Need to download the file, right?
You need to download some files. Have you gotten all four? Or?
Just 2022.
Okay. You've downloaded all four of them? Let me catch up and download the last two.
No, but the
There's a list of files right here,
okay.
and you need to go to CDDIS. And
I mean website.
I need to put the name of the files here or no?
no,
Okay.
you don't need to do anything there.
Okay.
So go to CDDIS.
Okay, I got it. What's the file names?
So go to the sessions webpage. Are you at the sessions webpage?
I'm here.
Okay. Find the first file is R1258. So go to that session.
Sorry. 258.
Uh-huh.
I got it. I'm downloading now.
And download the schedule file. And then you do that for the other ones.
File. I'm logging. Change the dates. And R. And 4, 5. Right.
Okay, so have you guys downloaded the files yet?
I'm downloading the 35 dates.
So I just took these files, the RS1s and the R4 kinds of sessions are meant to measure EOP. So I just picked 4 files over the last 20 years, and I picked them towards this beginning of the year. And once you have them, they're going to be in your downloads directory. And I am right now in the example SCED directory. So my suggestion is you go to that directory.
Okay, I download the all files.
And then we're going to copy these files from CDDIS. I mean, not CDDIS, but we're going to copy them from the download directory.
Samples. Sketch. So are you guys in the examples, SCED examples? Okay, do you see what I've typed there at the bottom? Yes. That should copy all of those files over to your directory. And I just did a listing of some files.
After the SPG, there's a dot.
There's a space and there's a dot. And that dot means copy it here. Okay. So
But I have been,
okay, do it.
but they are here. I don't know why they don't show up.
They're there. Okay.
Dial yes.
So now we've copied these 4 files, and these 4 schedules are actually things that we used. And we're going to use SCED, and then SCED is going to make a program that's a file that's used by the simulation program. And so we will type, we'll do the first one, SCED r1258.sced. And that opens it up. So if we look at this thing, we can see that it's what? 1, 2, 3, 4, 5, 6, 7 stations. And now you're going to type the command solve, S-O-L-V-E. And that's going to go through, and so if we get out of this, and yeah, and you do ls r1258.star,
there are two files there. There's the sched file and the .solve file. So see if you see that.
Okay.
Okay, so now we're going to do the same thing with the other three files. So you open them up with sched,
That
and then you type sched R4 514,
so
and then solve.
that 11.
Sorry, it was R54, but
R4514.
That so
And when you run solve, you're going to get some error messages. Ignore those.
that last file. Seven. So Professor, in last pad, I put the soap in running elevation tower lower.
Yeah, ignore that
Ah,
message
okay.
for the time being. I check your downloads area. Is it in your sched area?
it is in my knowledge, but the terminal, the link show.
So try doing this. Copy. Which one? R41415? That one?
451.
4514. Yeah. Copy 4514.sched to dot. Did it come? It worked. Okay. So let me know when you've made all the .solve files.
Finish.
You finished.
After like the dark in head and the soul, but I need to like
Type Q.
do it with the other.
Yeah, do it with the other ones. Okay, how's it going there? R11033.
O estrela para filtrar o que você quer achar. Vou pegar R.
Okay, when you're done, you should have all of these .sol files in your directory. You know, I have more than you did because I was playing around some. But we're going to copy them to the simple simul directory. So you type copy star.solve. And then you do // simple simul.
Okay.
And that should copy everything over there. Then let's change directory to that directory. CD simple simul. CD .. simple simul.
Okay.
And they should be in that directory. Do an ls star.solve, and you should see them there. Now we're going to set up simple simul to be ready to process 24-hour sessions. And we're going to do that copying simple simul 24hour.cfg to simple simul.cfg. So if I look at this file that we just copied, it contains information about how to process a session, how we're going to, what kind of parameters we're going to estimate. That's the partial file. It has a turbulence file, and the turbulence file is a model of the atmosphere. And then it has a directory called output directory. And got it?
Right.
So once you've done that copy, what I want, simple simul, let's see, Simple simul R1258.solve. And you should start to see something that looks like this. Bring it here.
But that's very slow in my computer.
I'm sorry. Oh, you don't do an LS. Just do simple simul.
No LS here.
No LS. Yeah, LS means list.
Not your fault.
Yeah.
And do it in another files?
Yes, do it on the other files.
No. We are doing new outputs, right?
Yeah.
I need to do this command for every file.
Yes. There's something wrong with R477, so don't do it for that. But do it for the others. Peace. R415, is there something wrong with that? Correct.
Great.
Okay.
Yes.
So two of the files it had problems with, and I'm not quite sure why, and I'd have to investigate. But if you look at the files R100, if you do a grep UT1, capital UT1 output star.text, or let's just look at this. Let's look at more output R11033 sim.text. So this tells me about how it set up the simulations and what the results of the simulations were.
Slash R11023 is
More output. E commit FMS when we
So do you see some, do you get that result? You see it?
yes.
Okay, I'm going to roll up the screen because I want to talk a little bit about some of what Simple Final is doing. And so Simple Simul is adding noise to the measurement, and it adds different kinds of noise. So it adds some thermal error, random noise, which is measurement noise. And so for each clock, it assumes that the clock is varying around like this. And it assumes that the clock is, that this follows a random walk process. And does anybody know what a random walk process is? Random walk.
Oh,
A random walk is described as like somebody's really drunk and they take one step in one direction, one step in another direction. And that's what it models for the clock, is random walk. And then for the atmosphere, it assumes that the atmosphere is bumpy and turbulent. So here's a picture of the atmosphere above the site. In some places it's going to have a bump, and other places will have a depression, and here will have a bump, and here will have a depression. And, you know, so this whole thing is rough. In our modeling, we assume that it's smooth, that if I look here and I look here, I see the same thing. But really what happens is if I look at different places, I have different kinds of bumps here. And there may be some overall, the atmosphere overall may be going up and down, but different parts of it are rough. So it assumes that I have this atmospheric roughness. And if you look at Simple Simul, when it's doing its calculations, the thing that takes the longest is to model the atmosphere. And if you look at it, the output of it, you know, say it's modeling the atmosphere at this station and at this station and this station, and that takes most of the time. So it will go through and then it will do this like 1,000 times. For each station, it simulates a clock 1,000. For each station, it simulates an atmosphere 1,000 times. And then it outputs two things. One is it outputs what the formal errors are. That is, how good are things if we had modeled things, everything correctly? And then it outputs the scatter in the estimate. And the scatter in the estimate is a more realistic number of what our real accuracy is. So let's go back to, I'm going to put this down. Okay. So if I look at this one session here, I look at my UT1 values. Let's see, can you see my mouse? Yeah. It has a sigma of this 0.9 microseconds. But the scatter is 6 microseconds. So a more realistic estimate for this is the scatter. And up here, it's telling you information about how it's modeling things. There's this parameter called CN, and that's a measure of the roughness of the atmosphere. And Simple Simul reads in a file that has these CN values and uses those. And so you could modify the CN values at different places if you wanted to get different sorts of answers. So that's one thing that you can do, is you can see, compare, what the formal errors are, which the sigma is, to the RMS. As I mentioned earlier, another question you can ask is, suppose that we change the parameterization. How is that going to affect things? So we're going to do a simple test where we're going to change the parameterization and then rerun 2 of these schedules to see which parameterization is better. So to do that, what I want you to, let's see, type this, cat simplesimul.cfg. So that is the configuration file. And this file up here is the file that it's using to say how it's parameterizing the data. So we're going to modify that file and parameterize the data a different way. Since I set up this file, I know what it's saying. It's saying I'm going to use 20-minute atmospheres and 30-second clocks. So I'm going to copy that file into my directory. And I'll type copy. So you see what I'm doing? I'm just copying it to something I'm going to call 24-hour test 1.txt. Okay?
Last opportunity, wait for or the value test test one.
Yep. Yep. Got it? Everybody's got it? I mean, the simplest thing is, as I said, to copy it up there. Over. Okay. Okay. Now what we're going to do is we're going to go into 24-hour test1.txt. Edit that. What? It's not there?
Your slash
Oh, I didn't have the hour. And if you go down here on lines 35, 36, 37, it tells you various things it's estimating. And if you go to line 48, it has this thing where it says stat all atmosphere B-spline every 20. And what that means is we're going to have, we're modeling that way, atmosphere is piecewise linear with breaks every 20 minutes. Let's change that to, first off, get rid of display highlighting. Instead of 20 minutes, let's do 120 minutes. So we're going to say the atmosphere changes every 2 hours instead of every 20 minutes. And for the clocks, we have something similar where we say 30. Let's also say that's 120 minutes. And save that. Okay. Now we're going to store this stuff in a different directory. So we want to say make dir output 2. Okay. Got that? Yeah.
It breaks change that again, change that together, right?
Pardon?
It breaks every 120 minutes, right?
Yeah, you can put that into the stuff that has the comment, the stuff that asks the exclamation mark is just comments.
Ah, okay.
So now, so we make this other directory where we're going to put the stuff because we want to compare the things. We don't want to overwrite what we did before. And let's go into edit the configuration file, simple simul.cfg. And we need to do two things. One is we need to change the partial file or the way we're parameterizing the data. So we can do that by putting an exclamation mark at the beginning of the line, and that comments it. This is the C sort of format. And then we'll say partial file 24-hour test1.txt. And the other change we need to make there is we change the output directory to output 2.
Can you repeat what you did?
One of the things we did is where it says partial file, we commented out the original partial file, which was this SGP, VLBR, blah, 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 20A, 30C by putting a exclamation mark at the beginning. And then we wrote in partial file 24-hour underscore test1.txt.
You can show the terminal, please.
I'm not sure what you're asking.
Show command line, please. Make it here. Okay, thank you.
Yes. I'm sorry, I can't hear you. The information. Oh, that comes from, there was a student in, from University of Vienna, and that was part of his thesis project. And that's based on radiosonde data of the atmosphere. And that assumes that it's the same in the summer and the winter, but it actually varies. So there is this branch of physics dealing with turbulence. And so this guy applied turbulence to the atmosphere. And in turbulence, turbulence theory says that something that happens here has some relationships to stuff that's nearby it, and it dies off as you go further away. And so that's the basic idea. And in terms of, you know, how rough it is, that depends on the specifics of the station that you're at. So what goes into it is things like, as you said, water vapor, stuff like that. And so you can base this on numerical weather models to get an idea for it. So one of the complaints about this is it's, you know, sort of theoretical. You're putting in a model for the atmosphere and you don't know how good the model is. But that's always the case. So have you guys all set to do the next run? Yes. Okay. So we've done two changes here. One is we're changing the partial file, which is a parameterization, and the other is we're changing the output directory. So let's do a save, and then get out of here.
The last change, teacher. What's the last change?
We changed the output directory.
Output directory.
So the output directory in simplesimul.cfg should now be output 2.
Okay.
So let's try typing, now that we've made these changes, simplesimul r11033.solve. And you can see that it's reading it in. Right now, it's sort of making synthetic atmospheres. And this code is written to use as many cores as it can find on your machine. So did you type it in? Is it done?
The same amount of information that
You don't show the same stuff?
yes, but no.
It's showing now.
Okay.
It's so confusing.
It showed that the stations, but not this delta T doesn't show.
Okay, it died, so that's why. So it's
No.
okay. Okay, you guys do it and it's working, going
Yes.
through? So I'm going to do grep UT1 output star R1033 sim.text. So this is what I get up here. And there are a couple of comments I have. One is, remember this first column here is the formal errors. And I'm estimating UT1 offset and rate. So the formal errors are 0.66, and the scatter is 7.33. So my formal errors have gone down, but my scatter has increased. Why has the formal errors gone down? The formal errors have gone down because I'm estimating fewer parameters. And anytime when you do least squares, if you estimate fewer parameters, your remaining parameters have lower formal errors. But on the other hand, if I compare the scatter, here my scatter is 7.33 microseconds when I had 20-minute atmospheres. Or when I have 2-hour atmospheres, my scatter is 6.37. So by parameterizing the atmosphere at finer detail, I actually make the UT1 estimates less sensitive.
Professor, what's the margin of error in this calculation?
I don't know. It roughly goes like how many simulations you do. I do it.
Because my calculus have a little bit chance.
Yes. Well, this stuff here, this stuff should be the same.
Yes.
This stuff.
Chance.
This is different. This number is going to be different each time you do it because you're doing random simulations. And every time you do a random simulation, you're getting different numbers. You had a question.
There's just one offset one and one rate in yours. That's for
You have just one? You did not do, you look at the top of it. Do you have output 2 and output here? So right there at the very beginning.
this it starts in the 1 and 2.
Okay, do an ls. And you should have a directory called output and a directory called output 2. And you do. You're lying. Look at, let me look at, bring it here. Okay. No, let me look at then. You need to change that to output 2. Because what happened was you overwrote what we did before. So the problem was that when we made this previous change, we wanted to make 2 changes up here. One was to change the partial file, 24hour.txt, and the other one was to change the output directory so that we put the stuff in a different directory. And Eric forgot to make the second change. So what happened was his results overwrote the first thing. But that is sort of an introduction to simulations. You can play around with the parameterization, try doing things, different kinds of things. You can write different schedules and use different networks, and then use simulation results to compare them. there is a person, Cynthia Thomas, who works at NASA. And one of her jobs is to design the networks for the coming year. And she does that by asking all the stations how much they can observe and what days they can observe. And then she generates different networks and tries to come up with networks that have the best results. And I think that's about it for me for today. So let's have our coffee break and go home early, if that's fine. Then tomorrow we'll meet. We'll have start off by having some discussion and some review. I'm going to give everybody a little quiz of some of the material we've covered. Then we're going to have a general discussion about next steps, and then we'll have pizza. Okay.
Professor, using the turbulence, have many courses of hardware or not?
I use the computer hardware. I use the code I've written is multi-thread.
Oh,
So it uses as many cores as there are that it can find.
whose parallel contains lines?
Yes. It does not use the graphics processor or things like that, but it just uses, most adult processors have many cores. So.
But the parallel hardware exercise extensive simulation. So it's necessary to most hardware.
Pardon?
In extensive simulation,
Mm-hmm.
NASA will have
Yes. Yes. They do much more complicated things than I'm doing. So everybody online, goodbye. It's been fun talking to you. See you tomorrow.